I'm Charles, and today I'd like to talk a bit about RAPIDS and Dask, two open source projects built around accelerating data science, and how they come together to power Dask SQL, a library that allows users to query tabular data using dataframe and SQL APIs on both CPU and GPU. So, for just over a year now, I've been working as a software engineer at NVIDIA on RAPIDS and Dask, focusing on the interactions between the two projects and how to ease some of the pain points in distributed computing on GPUs. I've also been maintaining Dask SQL for around 8 months now, and spent a lot of time working on its interactions with the RAPIDS-Dask ecosystem, exploring ways to improve its functionality and performance on both CPU and GPU. First, I'm going to go over some of the issues that have motivated projects like RAPIDS and Dask. Next, I'll give a brief look into what RAPIDS and Dask are and what they offer to Python data scientists. From there, I'll give a short demo of Dask SQL, showing how it works with these two projects to provide a solution to some of those data science problems. Finally, I'll dive into some of the technical work that's being done to get Dask SQL to where it is today. So, a lot of the issues around modern data science can be summed up in a few words. It's expensive and big. Computationally expensive queries require increasingly powerful hardware to be executed in a timely fashion. To compound upon this, these queries are typically being run on big data that can't be persisted in its entirety on local storage. The sum of this is that the average data scientist is typically not able to do the majority of their research on a standard laptop or PC. Often, we see large servers, cloud compute instances, or HPC utilized to perform this work remotely. Two popular strategies often suggested to handle big and expensive data science are scaling up and scaling out. Scaling up is essentially solving this big and expensive problem with a bigger and more expensive machine, relying on powerful hardware to enable or boost performance. While this is a trivial unblocker for the majority of workloads, it obviously comes with some drawbacks. First is cost. We don't want to pay more for hardware unless we absolutely need to, and ideally should be able to minimize the time that it's being used. Beyond this, more powerful hardware can come with different formats of developing and querying, which can be difficult to acclimate to. Scaling out is essentially sharding up our original problem into smaller problems to solve in parallel. While this can generally be less expensive than scaling up, it doesn't always solve the problem and comes with issues requiring new skills to develop and query. Parallel programming can be radically different from serial programming. Understanding the pros and cons of these strategies is a good way to contextualize the work being done within RAPIDS and Dask, which aim to ease the burdens of scaling up and scaling out, respectively. RAPIDS is an open source suite of libraries that provide end-to-end GPU data analytics through familiar PyData APIs. By mirroring ubiquitous Python data science libraries, for example, UDF for pandas and QML for scikit-learn, RAPIDS minimizes the time spent learning GPU programming. In most cases, all a user needs to do to enjoy performance gains is switch out the imported PyData library for its RAPIDS equivalent. This ease in switching between CPU and GPU code can also assuage issues of cost, making it relatively easy to prototype workloads on an accessible CPU machine before deploying to GPU. What if GPUs aren't available? What if we want to make use of pre-existing CPU hardware to tackle data science problems? In cases like this, we can turn to Dask. Dask is a library that takes a similar approach to RAPIDS in mirroring PyData APIs, with the focus being placed on distributed data analytics. At its core are a variety of parallelizable collections extending PyData interfaces, such as dataframes and arrays. These collections are backed by chunks of serial objects, such as pandas or UDF dataframes, which are only persisted into local memory on demand. When APIs are called on a collection, a graph is constructed of the tasks that need to be executed on the underlying serial data, which can be used as a plan to compute the operations in parallel. This graph can then be passed over to Dask Distributed, a dynamic task scheduler that assigns these tasks to workers on a distributed cluster. These workers can occupy a wide array of different hardwares: CPUs, GPUs, remote machines, and more. By leveraging existing PyData interfaces, Dask makes it easy to scale out existing data science workloads with minimal code changes. Additionally, Dask's flexible cluster system makes it easy to switch out the resources being used for execution, which can once again prove useful for prototyping queries on accessible hardware before deploying elsewhere. On their own, RAPIDS and Dask are great data science libraries that make it easy to accelerate existing workloads. But often, we don't just want to scale up or scale out. A healthy balance of both strategies can yield the most cost-efficient results. That's why folks at RAPIDS and Dask have been dedicated to collaboration so that multi-GPU users can get the best of both worlds. This work has culminated in RAPIDS libraries that extend the APIs of Dask to be optimized for GPU operations. Dask UDF re-implements several data frame operations, such as sorting and group bys, to take advantage of optimizations available to GPUs. Dask CUDA provides users with workers running on GPU, as well as offering a great deal of customization with respect to communication protocols between these GPUs, memory spilling to disk, and more. Coupled together, RAPIDS and Dask make it easy to unblock or accelerate data science workloads on a variety of hardware with little effort. That being said, up until now, the benefits I've been describing are targeting data frame users, when in reality, data frames are not the only way to query tabular data. In some cases, they aren't even the best way to interact with tabular data. While the data frame API is certainly mature, there are still several limitations to it that can make certain tabular operations difficult to express. For example, we can see in this code block that the limitations of typical data frame sorting algorithms force us to make several calls to achieve per-column null positioning. On top of this, it's still a relatively young API that data scientists may be unfamiliar with when migrating existing workloads to Python from other languages. Enter SQL, a mature domain-specific language for querying tabular data. In addition to providing a common ground for data scientists coming from several backgrounds, SQL also has functionality that can make some tabular data queries significantly easier to write out. Taking our previous example, we can see that the multiple data frame sort value calls can be achieved with a single SQL order by statement. Overall, SQL is a useful tool for data scientists with or without knowledge of data frames. And now, with Dask SQL, this is a tool easily accessible to Dask users. Dask SQL is a SQL parsing engine built on top of Dask data frame. Using it, we can register Python data frames as SQL tables, query them using standard SQL, and extend it using custom functions when needed. When a SQL query has been executed, we receive a Dask data frame, which can then be used for any additional querying we may require the data frame API for. This allows Dask SQL to either be used exclusively as a replacement for the data frame API, or in conjunction with it to do operations more easily defined as SQL statements. And being built on top of RAPIDS and Dask means that workloads depending on Dask SQL enjoy the same ease of scaling up and scaling out. This is something that's more easily demonstrated, so with that, I'll switch over to a demo. Before we start using Dask SQL, let's make sure to initialize a Dask cluster and connect it to a client. After doing this, all subsequent Dask operations will be run by the workers on this cluster. In this case, we'll be using Dask CUDA's local CUDA cluster so that my workers have access to the GPUs on this machine. Notice the logging messages we get on cluster initialization, which correspond to the initialization of Dask processes on each of the GPUs in this machine. With cluster initialization out of the way, we can now get started with Dask SQL by creating an instance of its core class, the context. In Dask SQL, a context essentially acts as an equivalent to a SQL database. It's where all tables and custom functions are registered, and it's the main interface through which queries can be executed using these tables and functions. Now all we need is data to query. Registering tables to a context can be done in a couple of ways, but generally the most flexible is using the createTable method. This takes as input a string table name and an object representing a table. This table object can be a variety of types, including pandas or QDF data frames, which will result in computations running on CPU or GPU respectively, Dask or Dask QDF data frames, tables stored on disk in conventional file formats such as CSV, Parquet, and ORC, and some of the more common interfaces used to interact with pre-existing databases in Python, such as SQL Alchemy connections or PyHive cursors. And with all the examples I've shown, we don't even need to pass through a GPU-specific object to get things running on GPU. Simply passing GPU equals true as an argument to create table will load in our table using Dask QDF. For the most part, this is where differences between CPU code and GPU code begin and end, making it very easy for us to flip a switch to enable or disable GPUs when needed. Now that we've got some data registered, it's time to query. This can be done using the SQL method, which takes as input a string SQL query, which is then parsed and executed, returning a Dask data frame if the query has a return value. Now let's take a look at one of the tables we've registered. So like standard Dask data frames, the results here are lazy and need to be computed manually to actually execute tasks on the cluster. We can also pass data frames directly to the SQL method using the data frame's keyword argument. This can be useful if we intend to switch back and forth between querying tables using the data frame and SQL APIs. When standard SQL functionality isn't enough, we can register custom user-defined functions to do exactly what we need. Dask SQL allows for column-wise and row-wise UDFs, as well as custom aggregations for column reduction. Column-wise UDFs take columns and scalars as input and return columns of an identical length. They can be registered using a register function method, which takes as input a callable Python function, a name to register it to, and data types for its inputs and outputs. Once registered, we can use this function like we would any standard SQL function. Column-wise functions are all good and well, but sometimes they aren't what we need. For example, if we need to access the values of individual rows as part of our function's logic, we'll find that the vectorized approach of Dask columns makes this impossible without manually computing the column mid-function. In this example, our column can't assert on a row-by-row basis which column is greater than or less than, and would raise an error if we attempted to pass table columns into it directly. For cases like this, we can rely on row-wise functions, which instead take a dictionary object as input that represents an individual row. Now we're operating on scalars instead of columns, and our original function's logic holds up. Row-wise functions can also be registered using register function, this time around specifying row UDF equals true. Keep in mind that performance can be impacted heavily by our choice of column or row-wise functions. This is primarily tied to how the underlying data frame libraries handle row-wise functions. For example, row-wise functions in pandas mean missing out on vectorized optimizations that would be made on column-wise functions. Thus, they tend to run slower than their column-wise equivalent. On the flip side, recent work has been done in UDF to make row-wise functions relatively performant, sometimes more so than their column-wise equivalent. Finally, we have aggregations, which are used to reduce a column to a single scalar. These can be used within the scope of aggregating queries, such as group by statement. These can be registered using Dask aggregation class, and registered with the register aggregation method, which works similarly to register function. Obviously, one major use case for tabular data is machine learning work. Thankfully, Dask SQL supports model creation, training, and prediction entirely in SQL, while still being flexible enough to incorporate into pre-existing Python ML code. If we already have a pre-existing Python model that's been trained, we can register this in our context using register model. This method works similarly to register table, additionally taking the names of the model's training columns as input. Alternatively, if we want to stay entirely in SQL, we can opt to create and train a model using the create model statement. This takes as input the absolute path to a Python model class implementing fit and predict, as well as the name of a target column in the table being used for training. From here, a registered table can be queried to provide training data for the model. Once a model is registered, predictions can be made using it with the predict keyword, allowing us to pass through a query providing data to test our model on. So up until now, I've mostly been focused on what Dask SQL can do and not how it does it. Obviously, it's important for data scientists to understand what operations their queries entail so that they can optimize as much as possible. Using the explain method, we can take a look at the specific SQL operations being executed for a given query. In this case, we can see this query generates 3 SQL tasks: a table scan to read in the data, an aggregation to compute the average of column X, and a projection to select this single aggregated column. If we want to get even more granular with task information, we can check the Dask attribute of the query's resulting Dask data frame. This will show us all the high-level Dask operations that will be executed by this query. Note that while we only had 3 SQL tasks to execute, this corresponds to much more Dask operations. This is because the limitations of Dask, coupled with the relative complexity of SQL querying logic, means we often require a number of workarounds in Dask's API to get the desired SQL result. This is a good place to transition into the past and ongoing work to improve Dask SQL's performance. A theme that I want to touch on while discussing this work is the idea that making things better in Dask SQL also makes things better for the wider RAPIDS-Dask ecosystem. Because of its concentrated usage of Dask dataframe APIs, issues faced when developing Dask SQL often reflect larger issues faced by Dask. Enhancement requests in Dask SQL often snowball into larger initiatives to improve the overall functionality of Dask, so that these improvements ripple out to the larger community instead of just Dask SQL users. And, as a hardware-independent library, efforts to get Dask SQL working and performant on CPU and GPU push Dask closer towards hardware independence, making it so the difference between Dask code running on CPU and GPU are negligible to non-existent. To contextualize this work, let's go over what happens when a query is executed. First, queries must be parsed and converted into a relational algebra that can be read in Python. We achieve this by passing them to Apache Calcite's SQL parser. Once this parsing is complete, we're left with a list of SQL tasks to execute to get the result of our query. These tasks are then mapped to Dask API calls to apply to the input table, ultimately returning to the user a Dask data frame. So, when we're thinking about how to improve performance, two good places to start are with how we parse queries and how we implement SQL tasks in Dask. Currently, work has been ongoing to switch out Dask SQL's Calcite parser for Apache Arrow Data Fusion. The reasons for this are based both in performance and stability. By using Calcite for query parsing, we introduce a Java virtual machine instance that must be started up whenever Dask SQL is imported. In addition to bloating import time, which slows down query execution if Dask SQL needs to be imported by Dask workers, this also introduces conflicts between the Java and Python error handling, which can manifest as segmentation faults depending on when Dask SQL is imported in a workload. By switching to data fusion, we're able to avoid these issues while also enjoying the performance benefits of a lighter weight parsing engine. Additionally, collaboration with data fusion developers means that many of the obstacles we've encountered in making the migration have motivated changes upstream in data fusion to improve for the overall community. Right now, there's still much work to be done, and not all SQL statements are supported, but I'm hopeful in the near future we'll be able to begin incorporating this work into new releases. Now I'd like to talk about the work being done to improve the Dask implementations of SQL tasks, in particular, sorting and filtered I/O. SQL sorting is complex and difficult to emulate in Dask, allowing a user to sort a table by multiple columns, each with a unique sort order and null position. In contrast, at the time that we began development on Dask SQL, both Dask and Dask UDF sort algorithms lacked support for sort order or null position, and Dask CPU only supported single-column sorts. I'd like to emphasize here that the lack of this functionality in Dask was by no means a design choice. The ability to sort a table by multiple columns, with the option to customize sort order and null handling, is a foundational aspect of a dataframe API's sorting algorithm. The lack of these features in Dask reflected the limitations of its sorting algorithm, which may have been an ongoing problem that simply didn't get much attention until Dask SQL made extensive use of it. Given these limitations, Dask SQL initially used costly workarounds to achieve SQL sorting through Dask, specifically the custom sorting function shown here alongside its corresponding task graph. This function made use of several Dask indexing and concatenation tricks to achieve sort order and null position handling. In addition to introducing several pre- and post-processing steps to the actual sort operation, this function is also significantly more computationally expensive than a standard Dask sort values call. When looking into how we can improve sorting, it was easy to see that adding sort order and null position handling to Dask's sorting API would allow us to simplify or even remove this function altogether. Feature requests were opened and work was started to do this, and by the December 2021 releases of Dask and Dask UDF, we were able to take advantage of this functionality to remove the majority of Dask SQL's custom sorting logic, greatly improving the performance of order by statement. On top of this, these additional features greatly enhance the sorting experience for Dask data frame users on CPU and GPU alike. There's still lots of work to be done to further improve sorting. At the top of our list is adding support for multi-column sorts to Dask on CPU. This would allow us to remove some GPU-specific code in Dask SQL used to handle differences in sorting behavior between Dask and Dask UDF, as well as vastly improving the Dask sorting API for CPU. It would also allow us to move the sorting logic of Dask UDF into mainline Dask, moving Dask one step closer to hardware independence. This functionality is currently blocked by dataframe APIs that are not currently available in Pandas, specifically multi-column quantile and search sorted functions. Work is ongoing to scope out and implement this functionality. Next up would be to expand the sorting APIs of QDF and Pandas to support per-column null positions. This would allow us to factor out the remaining custom sorting logic in Dask SQL, while also making it easier to translate SQL order by statements to dataframe API call. Now I'd like to switch over to the work we've been doing to improve filtered I/O operations. To give a motivating example, let's say we want to load in a table from disk and perform operations on it, on a subset of it. Our table is large, too big to fit into memory in its entirety, or even in smaller chunks, and the subset we require is relatively small. It would be great if instead of having to load the table fully into memory before filtering, we could load in only the filtered subset we need. This is preferable for a variety of reasons. On top of reducing memory usage and improving performance, this would cut down on expensive I/O and networking times when working with remote data. This is particularly important for GPU users, where storage and networking are often the biggest bottlenecks to performant computation. Thankfully, filtered I/O is something that Dask and Dask UDF already support. When using certain I/O functions, such as read parquet, users can pass a list of filters to apply to the table, as well as a list of columns to read from it. Dask will then use the metadata of the table to read in only the requested data. While this functionality is nice and allows for improved performance on filtered tables in Dask SQL, it still requires some foresight to be used effectively. A user needs to know beforehand what columns and rows from a table are needed for follow-up computation. If additional columns or rows are required, the original create table query must be revised and rerun, incurring avoidable I/O and networking fees. What would be even better is if Dask SQL implemented predicate pushdown and column projection, detecting if a user is attempting to filter a table read in from disk, replacing the separate filter and read operations with a single filtered read operation. This would allow us to replace relatively complex create table with queries with vanilla create table calls, knowing that subsequent queries would implicitly apply their filters to the underlying Dask I/O operations. To enable these features, work was done in Dask SQL to add opt-in predicate pushdown optimizations, and in Dask to extend its implementation of column projection to work better in conjunction with predicate pushdown. With this work merged in, any column and row filtering queries executed immediately after reading in a table from disk will be optimized into a single I/O operation if possible. This makes it easier to compose queries on large filtered tables without having to worry about high memory usage or networking fees. Work to improve filtered I/O in Dask and Dask SQL is ongoing. In the short term, progress is being made to move the predicate pushdown logic in Dask SQL upstream to Dask, where it can be taken advantage of by dataframe users. At the same time, work is being scoped out across Dask and Dask SQL to support predicate pushdown for more filtering cases, such as list containment. In the long term, discussions are being had around Dask's task graph system to make it easier to introduce optimizations like this moving forward. I'm really excited to see this work come to fruition. I know that it'll greatly benefit the Dask community. In conclusion, RAPIDS and Dask are great additions to the data scientist's toolbox to accelerate and unblock workload. And with the introduction of Dask SQL, they can be used in an even wider array of scenarios. I would encourage anyone here interested in this package to give it a try, and feel free to chime in our GitHub with any issues you encounter. I'd also like to give a special acknowledgement to Nils Braun, the creator of Dask SQL. Though he's no longer doing regular maintenance on the project, without his initial efforts, we wouldn't have anything to build off of, so we're immensely grateful to him. And yeah, that about wraps things up. Thanks a lot for taking the time out.
Okay, we have a couple do number one by JD. You mentioned filtering, group by, sorting. Do large and memory intense joins also benefit from RAPIDS or Dask?
Yeah, I would say so.
Oh, okay. That's it?
Yeah, I'd say, yeah.
Okay. Is there a good way to parameterize Dask SQL queries? Are there guards against SQL injection attacks?
Right now, our parameterization of Dask SQL queries is pretty limited to string formatting in Python. We haven't taken too much time to think about guards against SQL injection attacks right now, though that is a valid concern.
Is this something that can be used as sort of middleware to reduce costs between Power BI queries and BigQuery data lakehouse?
I can say, honestly, I'm not too familiar with that software, and so I can't really answer that question.
Martin is asking, do you have plans to overcome the need to write the whole SQL query as a string? Or is there some work in order to improve the user experience when writing SQL queries?
Not currently, although that is a valid thing that we should probably open an issue to think about.
Xavier is asking, can we use column-wise and row-wise UDFs at the same time?
Is the question, I suppose, can we use those functions in conjunction with one another? I believe the answer is yes.
I think the spirit of the question is you have a data frame like this size, and it goes down to a smaller subset, like you lose rows and columns, for example.
Mm-hmm. I'm not entirely sure.
Okay. How can we use Dask SQL with distributed computing where data is also distributed?
I guess I would like clarity on the idea of distributed data here.
Okay. Let's say I guess maybe the question here might be, how does this work with different file storages, for example?
Different what storage?
Like file storages or data sources?
I'm not sure.
Okay. Can we use Xarray with Dask for multi-column indexing?
We haven't looked into Xarray integrations yet, though that is a good place to explore.
Okay. It seems like we have one more question coming in. Just wanted to ask if anyone in the room also has questions, maybe, that doesn't have a laptop. Doesn't seem like it. Okay, I think we're done with all the questions. Yeah, if you want to chat with Charles, I guess feel free to approach him as well. And with that, thank you everyone, and let's give Charles a round of applause.